Autonomous vehicles represent one of the most transformative technologies of the 21st century. Defined broadly as vehicles capable of sensing their environment and operating without human intervention, AVs are being hailed as the future of transportation. These vehicles use a combination of sensors, cameras, radar, and artificial intelligence to navigate, identify obstacles, and make decisions in real time, fundamentally altering how people and goods move across cities and countries. The impact of autonomous vehicles is expected to be profound, touching nearly every facet of daily life, from reducing traffic accidents and lowering transportation costs to reshaping urban infrastructure. As this technology continues to mature, it is poised to disrupt traditional industries like automotive manufacturing, logistics, public transportation, and urban planning, while also raising significant ethical, regulatory, and societal questions. The idea of autonomous vehicles has been around for decades, with early concepts appearing in science fiction novels and futuristic films. However, it wasn't until the 1980s that serious research began. Projects such as Carnegie Mellon University's NAV Lab and Mercedes-Benz's autonomous driving experiments laid the groundwork for modern AV development. The real breakthrough came in the early 2000s with the advent of more sophisticated sensors and the development of machine learning algorithms. The DARPA Grand Challenge in 2004, a competition organized by the US Department of Defense, accelerated research by encouraging teams to develop fully autonomous vehicles capable of navigating difficult terrain. While none of the entrants completed the first challenge, it ignited widespread interest in AV research, eventually leading to significant advancements. Over the past decade, the AV industry has gained momentum, with major automakers, tech companies, and startups pouring billions of dollars into the development of self-driving cars, drones, and delivery robots. Tesla, Waymo, a subsidiary of Alphabet, and Uber are just a few of the key players at the forefront of this revolution. The development of AVs has not been without challenges, but the progress made so far indicates that a fully autonomous future is no longer a distant dream, but an imminent reality. Self-driving cars operate along a spectrum of automation, defined by the Society of Automotive Engineers, SAE, into 5 levels. Each level represents a higher degree of autonomy, culminating in level 5, where a vehicle is entirely autonomous, capable of operating under all conditions without any human intervention. Level 1, Driver Assistance. At this level, the driver remains in control of the vehicle but can be assisted by systems such as adaptive cruise control or lane-keeping assistance. Level 2, Partial Automation. Vehicles at this level can control both steering and acceleration, deceleration, but the driver must remain engaged and ready to take over at any time. Level 3, Conditional Automation. The vehicle can handle most driving tasks, but the driver must be prepared to intervene if the system encounters an issue it cannot handle. Level 4, High Automation. The vehicle is capable of fully autonomous driving under certain conditions, such as in a specific area or under specific weather conditions. No driver intervention is required in these circumstances. Level 5, Full Automation. The vehicle is fully autonomous in all situations and conditions. There is no need for a human driver at any point. As of 2024, most commercially available AVs are at Level 2 or Level 3, with limited deployments of Level 4 vehicles in controlled environments, such as Waymo's autonomous taxi service in certain US cities. It will be further discussed about specific technological advances, real-world applications, regulatory considerations, and future implications of autonomous vehicles in various industries. At the heart of every autonomous vehicle lies a complex array of sensors and hardware, enabling it to perceive its surroundings in real time. These technologies are crucial for understanding the environment, detecting obstacles, and making decisions about how to navigate safely. LiDAR, light detection and ranging. LiDAR uses lasers to create high-resolution 3D maps of the vehicle's surroundings. By emitting laser pulses and measuring the time it takes for them to reflect off objects, LiDAR generates accurate distance measurements. This technology is essential for recognizing road features, such as lanes, curbs, pedestrians, and other vehicles. Its high precision makes it a key component in many AV systems. However, LiDAR systems can be expensive, and their performance can degrade in adverse weather conditions like fog, rain, or snow. Radar. Unlike LiDAR, radar uses radio waves to detect the speed and distance of objects. Radar is particularly good at functioning in poor weather conditions and during nighttime. While it doesn't provide the same high level of detail as LiDAR, radar excels in detecting moving objects, such as other vehicles or cyclists, making it an essential tool for collision avoidance and tracking objects at high speeds. Cameras play a critical role in object recognition and scene understanding. AVs typically use multiple cameras to gain a 360-degree view around the vehicle, enabling them to interpret road signs, traffic lights, pedestrians, and other vehicles. The data from cameras are processed using image recognition algorithms, allowing the vehicle to see and make sense of its environment. Advances in deep learning have significantly improved the accuracy of camera-based perception systems, though challenges remain, particularly in low-light or visually complex environments. Ultrasonic sensors. These are used for detecting objects in the vehicle's immediate vicinity, such as during parking maneuvers or while navigating tight spaces. While less advanced than LiDAR or radar, ultrasonic sensors are cost-effective and highly reliable for short-range detection. Each sensor has its strengths and weaknesses, which is why most autonomous vehicles use a combination of LiDAR, radar, cameras, and ultrasonic sensors to ensure a comprehensive understanding of their surroundings. By fusing data from these multiple sources, AVs can make more accurate and informed decisions about how to drive safely. While sensors capture data from the physical world, it's the software and artificial intelligence systems that interpret this data and make decisions in real time. Machine learning, particularly deep learning, has been instrumental in training autonomous vehicles to recognize objects, predict movements, and respond to changing environments. Object detection and classification. Using data from cameras, LiDAR, and radar, machine learning algorithms are trained to detect and classify objects such as pedestrians, cyclists, vehicles, and road signs. This ability to recognize and categorize objects is crucial for the vehicle to understand what is happening around it. Path planning. Once the environment has been perceived, the vehicle must decide on the best course of action. Path planning involves calculating the safest and most efficient route for the vehicle to take, considering factors such as traffic conditions, road layout, and potential obstacles. This process happens continuously as the vehicle moves, with the artificial intelligence adjusting the path in real time based on new information. Predictive modeling. One of the challenges in AV development is predicting the behavior of other road users. Autonomous vehicles must not only detect other vehicles or pedestrians but also anticipate their next move. For example, if a pedestrian is approaching a crosswalk, the AV must predict whether they will cross the street and adjust its actions accordingly. This requires complex algorithms that factor in historical data and contextual clues. Control systems. Once the vehicle has identified its surroundings and planned a path, control systems take over to execute the necessary driving maneuvers. These systems manage steering, acceleration, and braking, ensuring the vehicle follows its planned route safely. The combination of these software elements, object detection, path planning, predictive modeling, and control systems, enables AVs to navigate complex environments. However, the variability and unpredictability of real-world conditions present ongoing challenges for developers. A key technology that will enhance the capabilities of autonomous vehicles is vehicle-to-everything, V2X, communication. V2X allows vehicles to communicate with other vehicles, infrastructure, pedestrians, and even the grid, creating an interconnected network that can significantly improve safety and traffic flow. V2V, vehicle-to-vehicle. Through V2V communication, autonomous vehicles can exchange data with nearby vehicles. For example, if a car several miles ahead detects a traffic jam or accident, it can send a warning to other vehicles, allowing them to adjust their routes or speeds accordingly. V2V also enhances safety by enabling vehicles to coordinate their movements, reducing the likelihood of collisions. V2I, vehicle-to-infrastructure. In this form of communication, vehicles interact with road infrastructure, such as traffic lights, road signs, and smart city systems. V2I can help AVs optimize their routes by receiving information about traffic conditions, road closures, or parking availability. In the future, smart cities equipped with V2I will play a vital role in the seamless operation of autonomous vehicle fleets. V2P, vehicle-to-pedestrian. To improve pedestrian safety, AVs can use V2P communication to detect and interact with pedestrians carrying smartphones or wearing connected devices. This can alert the vehicle to the presence of pedestrians in areas where visual detection might be limited, such as around corners or in low visibility conditions. V2G, vehicle to grid. As electric vehicles, EVs, become more prevalent, V2G communication enables vehicles to exchange data with the electrical grid. This allows autonomous electric vehicles to optimize charging patterns, contribute to grid stability, or even provide power back to the grid during peak demand periods. V2X communication enhances the situational awareness of autonomous vehicles, allowing them to make more informed decisions and improving overall road safety. However, it also raises challenges in terms of cybersecurity and data privacy, which must be addressed to prevent malicious actors from exploiting this technology. As the vast majority of autonomous vehicles are expected to be electric, advancements in battery technology and energy efficiency are critical for the widespread adoption of AVs. Currently, electric vehicles, EVs, face limitations in range, charging time, and battery life, all of which impact the viability of large-scale autonomous vehicle fleets. Solid-state batteries. One of the most promising advancements in battery technology is the development of solid-state batteries. These batteries use a solid electrolyte instead of a liquid one, offering greater energy density, faster charging times, and improved safety. Solid-state batteries could significantly extend the range of electric autonomous vehicles, making them more practical for long-distance travel and reducing downtime for charging. Wireless charging. Autonomous vehicle fleets could benefit from wireless charging technology, which allows vehicles to charge without needing to be plugged in. Wireless charging pads embedded in parking lots or even roadways could enable EVs to charge while idle or on the go, reducing the need for human intervention in fleet management. Energy harvesting. Some autonomous vehicles are exploring the use of energy harvesting technologies, such as solar panels integrated into the vehicle's design. While this won't be the primary energy source, it could supplement battery power, particularly in sunny regions or for vehicles that spend a lot of time parked outdoors. Fleet management and battery swapping. For large fleets of autonomous delivery vehicles or taxis, centralized fleet management systems could optimize battery usage by scheduling charging times or even utilizing battery swapping stations where depleted batteries are replaced with fully charged ones in minutes. This could minimize downtime and ensure fleet availability. The combination of these energy innovations will be critical to the long-term viability of autonomous electric vehicles, particularly in the commercial sector where uptime and range are essential factors for profitability. Autonomous drones, or unmanned aerial vehicles, UAVs, represent a significant advancement in autonomous vehicle technology, particularly in areas like delivery services, surveillance, and even passenger transport. The autonomy of drones relies on many of the same principles as self-driving cars, but with additional considerations for three-dimensional navigation and flight dynamics. Flight control systems. Autonomous drones are equipped with sophisticated flight control systems that manage takeoff, navigation, obstacle avoidance, and landing. These systems use inputs from GPS, accelerometers, gyroscopes, and magnetometers to maintain stable flight and navigate between waypoints. Autonomous navigation. Drones use various sensors to navigate autonomously. GPS is often used for broad positioning, but more precise navigation requires additional sensors like LiDAR, cameras, and radar. Autonomous drones must also account for airspace regulations, obstacles like buildings or trees, and dynamic changes in the environment, such as weather conditions. Object detection and collision avoidance. Similar to self-driving cars, drones use sensors to detect obstacles and avoid collisions. However, because drones operate in 3 dimensions, this task is more complex. Advanced algorithms help drones predict the movement of objects in their path, such as other drones, birds, or moving vehicles. AI and machine learning in drones. AI is increasingly being integrated into drone systems to improve their decision-making capabilities. Machine learning models can help drones recognize landmarks, adapt to environmental changes, and optimize flight paths for efficiency. This is especially important for drones used in delivery services, where factors like weather, airspace congestion, and dynamic obstacles must be considered in real time. The deployment of autonomous drones has expanded into numerous industries, each leveraging the unique capabilities of UAVs for a range of practical and innovative applications. These aerial vehicles are expected to play a key role in transforming logistics, agriculture, surveillance, and emergency response efforts. E-commerce and last-mile deliveries. Companies like Amazon, UPS, and Google's Wing have been pioneering the use of autonomous drones for delivering small packages directly to customers. The potential to reduce delivery times, particularly in densely populated urban areas or remote locations, is one of the key advantages. Drones can bypass ground traffic and deliver goods more quickly and efficiently than traditional delivery vehicles. This last-mile delivery solution has the potential to reshape logistics and e-commerce, making deliveries faster, cheaper, and less reliant on human labor. Food and medical supplies. Drones are increasingly being used to deliver time-sensitive products such as medical supplies, blood donations, vaccines, and even meals. During the COVID-19 pandemic, autonomous drones were employed to transport medical equipment and medications to quarantine zones and rural communities where access to hospitals was limited. These applications demonstrate how drones can fill gaps in healthcare logistics, providing critical services in emergency situations. Public safety and law enforcement. Autonomous drones equipped with high-definition cameras, thermal imaging, and AI-based recognition software are now widely used by law enforcement agencies for surveillance and crime prevention. Drones can patrol large areas more effectively than human officers and can be deployed quickly in response to emergencies. Drones are also employed in search and rescue operations, as they can cover wide territories and scan difficult-to-reach areas to locate missing persons or assess dangerous environments, such as after natural disasters. Infrastructure and facility monitoring. For industries that rely on critical infrastructure, such as energy companies and large manufacturing plants, drones are being used to perform routine inspections of pipelines, electrical grids, and railways. Autonomous drones can access hard-to-reach places, reduce inspection costs, and detect potential hazards, like leaks or structural damage, before they become major issues. Crop monitoring. Farmers are increasingly turning to autonomous drones to monitor their crops. Equipped with multispectral and thermal cameras, drones can assess crop health, detect diseases, and optimize irrigation practices. By capturing aerial images and data, these drones allow farmers to take action based on precise information, leading to more efficient farming practices and increased crop yields. Aerial spraying and seeding. In large-scale agriculture, drones are now being used to spray pesticides and fertilizers across fields with remarkable accuracy. Some drones are even capable of planting seeds in specific patterns based on data analysis of soil conditions. This reduces the need for human labor and heavy machinery, which can be costly and inefficient for smaller farms. Natural disaster relief. In the aftermath of natural disasters like earthquakes, hurricanes, or floods, autonomous drones play a critical role in assessing damage and delivering aid. These drones can quickly survey affected areas, providing real-time data to emergency responders, and can drop off essential supplies such as water, food, and medical kits. Drones can also be used to identify survivors trapped in debris or cut-off areas, assisting in faster rescue efforts. Firefighting. Autonomous drones are also being used to support firefighting efforts, particularly in large forest fires. Equipped with thermal sensors, drones can identify hotspots that are difficult to detect from the ground and help firefighters develop better strategies for containing fires. Additionally, in urban fire scenarios, drones can safely navigate buildings to search for victims or detect fire spread patterns. One of the key barriers to the widespread adoption of autonomous drones is the regulatory framework that governs their operation. Different countries have varying approaches to regulating the use of drones, and issues such as airspace management, privacy concerns, and safety requirements must be addressed to ensure the safe integration of drones into everyday life. Low-altitude airspace regulation. Drones typically operate in low-altitude airspace, which is relatively unregulated compared to higher commercial airspace used by traditional aircraft. However, with the increasing number of drones in the skies, managing this low-altitude airspace has become a priority. The development of air traffic management systems specifically for drones, such as the Unmanned Aircraft System Traffic Management (UTM), proposed by NASA, aims to create a standardized approach to managing drone operations and preventing collisions. Beyond visual line-of-sight operations, currently, many countries require drones to remain within the operator's line of sight for safety reasons. However, for autonomous drones to realize their full potential, particularly in delivery services, regulations need to evolve to allow beyond visual line-of-sight operations. Several pilot programs are being tested globally to enable flights under strict safety guidelines, which could pave the way for widespread adoption in the near future. Data collection and surveillance. One of the most contentious issues surrounding autonomous drones is the concern over privacy. Drones equipped with high-resolution cameras and other sensors can capture data on individuals, property, and activities, raising concerns about unauthorized surveillance. Regulatory bodies are working to establish guidelines on how data collected by drones should be stored, used, and shared, but achieving a balance between innovation and privacy protection remains a challenge. Cybersecurity. Autonomous drones are highly dependent on communication networks, GPS, and onboard software systems. This makes them vulnerable to cyber attacks, such as hacking or GPS spoofing, where the drone is tricked into thinking it's in a different location. Robust cybersecurity measures are needed to ensure the integrity and safety of autonomous drone systems, particularly as they are integrated into critical sectors like emergency services or defense. Collision avoidance systems. Ensuring that drones can avoid obstacles, both stationary and moving, is a primary safety concern for regulators. Autonomous drones must be equipped with reliable collision avoidance systems that can detect and react to unexpected obstacles, such as birds, other drones, or buildings. These systems must be thoroughly tested and proven safe before large-scale drone deployment is allowed. Certification and pilot licensing. While autonomous drones aim to reduce human intervention, many jurisdictions still require drone operators to hold specific certifications or licenses. This is especially true for commercial drone operations. As the technology advances and drones become more autonomous, regulations will need to adapt to account for fully autonomous systems where human pilots may no longer be necessary. Autonomous drones are poised to revolutionize supply chains and logistics by increasing efficiency, reducing delivery times, and lowering operational costs. The integration of drones into logistics networks is expected to optimize the movement of goods, particularly in the last mile of delivery, the final leg of the supply chain where goods are delivered to the customer. Same-day and on-demand delivery. Autonomous drones have the potential to enable same-day or even on-demand delivery services, allowing consumers to receive their orders within hours of purchase. This is particularly valuable for industries such as retail and food services, where fast delivery can be a competitive advantage. Rural and remote deliveries. In regions where traditional delivery methods are impractical or costly, such as rural or remote areas, autonomous drones can provide a much-needed solution. Drones can bypass poor road conditions and long travel distances to deliver essential goods quickly and at a lower cost. Reduced labor costs. One of the key benefits of using autonomous drones in logistics is the reduction of labor costs. With drones handling deliveries autonomously, companies can reduce their reliance on human drivers and delivery personnel, lowering overhead costs and potentially passing savings on to consumers. Energy efficiency. Drones are generally more energy efficient than traditional delivery vehicles, particularly for short-distance deliveries. Electric drones produce fewer emissions than gasoline-powered delivery trucks, making them a more sustainable option for last-mile deliveries. Airspace congestion. In urban areas, where space is already limited, managing the airspace for autonomous drones will be a significant challenge. As more companies deploy drones for deliveries, there is a risk of airspace congestion, which could lead to safety issues and delays. Effective air traffic management systems for drones will be critical to mitigating these risks. Noise and public acceptance. Drones, particularly those used in urban environments, can generate noise, which may lead to public resistance to their widespread use. Finding ways to reduce noise levels or developing quieter drone technologies will be important for gaining public acceptance and ensuring that drone deliveries do not disturb residential areas. As cities continue to expand and consumer expectations for fast and convenient delivery grow, the concept of autonomous ground-based delivery robots has emerged as a viable solution for the last mile of logistics. These small, wheeled robots are designed to transport goods from distribution centers or local stores directly to customers' doorsteps. Major companies such as Amazon, Starship Technologies, and Postmates are leading the way in developing and deploying these robots in cities around the world. Design and functionality. Delivery robots are typically equipped with cameras, sensors, GPS, and AI algorithms to navigate city streets, avoid obstacles, and deliver packages to their intended destinations. These robots are often used for small parcel deliveries, such as food, groceries, or e-commerce items, and are designed to operate autonomously, though many are still monitored remotely by human operators. Cost-effective solution. One of the main advantages of delivery robots is their cost-effectiveness. Unlike human couriers, robots can operate 24/7 without the need for wages, breaks, or benefits, making them an attractive option for businesses looking to reduce delivery costs. Moreover, these robots are powered by electricity, making them a more environmentally friendly alternative to traditional delivery vehicles. Their ability to navigate sidewalks, crosswalks, and even some roads while delivering goods efficiently makes them a practical solution for short-distance deliveries. Here's how they are being deployed and integrated into the modern logistics landscape. One of the biggest challenges in e-commerce is the cost and complexity of last-mile deliveries, which account for a significant portion of the total logistics cost. Delivery robots provide a solution by autonomously transporting packages from local distribution hubs to customers' doorsteps, especially in densely populated urban areas. Retail giants such as Amazon and Alibaba are investing heavily in autonomous delivery technologies, and robots have been trialed in major cities to deliver groceries, parcels, and other items. Companies like Starship Technologies and Postmates have partnered with local grocery stores, restaurants, and retailers to offer on-demand delivery services using robots. These partnerships are particularly popular for food deliveries, allowing businesses to reduce reliance on human couriers while providing customers with fast, reliable service. For instance, autonomous delivery robots have been used in university campuses, corporate offices, and urban neighborhoods for quick meal and grocery deliveries. Automation of warehouses. The rise of autonomous delivery robots is closely tied to the automation of warehouses and distribution centers. Robots are not only being used for last-mile delivery but also within warehouses to pick, pack, and transport goods. These robots, often called automated guided vehicles, AGVs, or autonomous mobile robots, AMRs, use advanced navigation systems and artificial intelligence to efficiently move items around a warehouse without human intervention. They play a critical role in speeding up the fulfillment process, reducing human labor, and increasing operational efficiency. Integration with drones and AV fleets. In some logistics models, delivery robots are integrated with autonomous delivery drones and vehicle fleets to form a seamless supply chain ecosystem. For example, a self-driving van might carry multiple robots and drones, each responsible for delivering packages to nearby customers. Once the van reaches a central point, robots can be deployed to complete the final leg of deliveries, while drones handle deliveries to harder-to-reach locations such as high-rise buildings. Starship Technologies, one of the pioneers in the delivery robot space, Starship Technologies has deployed its robots in several cities and campuses around the world. Starship Technologies, one of the pioneers in the delivery robot space, Starship Technologies has deployed its robots in several cities and campuses around the world. The company's robots use AI, GPS, and a range of sensors to navigate sidewalks and deliver groceries, meals, and packages to customers within minutes. These robots can be remotely monitored and are equipped with lockable compartments that customers can unlock using a mobile app. Amazon Scout. Amazon Scout robots are autonomous delivery devices designed to complement the company's existing delivery network. These robots operate at walking speed, delivering packages to customers' homes while navigating the suburban and urban landscape. Amazon is testing these robots in various US cities, with plans to expand their use as part of its last-mile delivery strategy. Nuro is another notable player in the autonomous delivery space, focusing on self-driving delivery vehicles rather than sidewalk robots. These vehicles, although larger than traditional delivery robots, are smaller than conventional delivery vans and are specifically designed for urban deliveries. Nuro has partnered with retailers like Kroger to deliver groceries and other goods directly to customers. One of the key technological challenges for autonomous delivery robots is navigating complex and dynamic urban environments. Robots must be able to navigate sidewalks, avoid pedestrians, obey traffic signals, and handle unexpected obstacles, all while delivering goods in a timely manner. This requires sophisticated AI algorithms, sensors, and real-time path planning systems. Delivery robots rely on a variety of sensors, including cameras, LiDAR, ultrasonic sensors, and GPS, to perceive their surroundings. Sensor fusion combines data from these multiple inputs to create a detailed map of the environment, allowing the robot to detect obstacles and plan its movements accordingly. For example, a delivery robot must be able to detect and avoid pedestrians, dogs, bicycles, and other obstacles commonly found on city streets. The use of AI-based perception systems enables robots to interpret real-world data, such as distinguishing between different types of obstacles, e.g., recognizing that a pedestrian is moving versus a parked bicycle. This real-time decision-making is crucial for ensuring safe and efficient navigation, especially in crowded urban areas where there is constant foot traffic. Route optimization. One of the key tasks of an autonomous delivery robot is determining the most efficient path to reach its destination. AI-powered path planning algorithms analyze real-time traffic, pedestrian movement, and road conditions to optimize the route. For instance, if the robot detects a blocked sidewalk, it can reroute itself to take an alternative path without human intervention. Obstacle avoidance. In dynamic environments, delivery robots must be able to react to unexpected obstacles. AI systems use predictive modeling to anticipate the movement of objects and plan around them. For example, if a robot encounters a pedestrian walking a dog, it will predict the pedestrian's likely path and adjust its speed or direction to avoid a collision. Human-robot interaction. In some cases, delivery robots need to interact with people, especially when delivering packages directly to a customer's door. AI systems are being designed to handle these interactions smoothly. For example, the robot can notify the customer of its arrival through a smartphone app, and the customer can unlock the package compartment once it reaches their home. While autonomous delivery robots are designed to operate without human intervention, most systems include real-time monitoring and remote assistance capabilities. In cases where the robot encounters a complex situation it cannot resolve autonomously, such as a road closure or technical issue, a human operator can take control of the robot remotely to assist in completing the delivery. This hybrid approach ensures that deliveries remain efficient even in unpredictable environments. The success of autonomous delivery robots depends not only on their technological capabilities but also on public acceptance and safety. As these robots become a common sight in cities, their integration into daily life must be seamless and non-intrusive to avoid potential backlash from communities. Trust in automation. One of the primary challenges for autonomous delivery robots is gaining the trust of the public. People may initially be skeptical or uncomfortable with the idea of robots delivering packages, especially if they are not familiar with how the technology works. Education campaigns and positive interactions with these robots will be essential for building trust and ensuring widespread acceptance. User experience. The convenience and reliability of delivery robots are also crucial for consumer acceptance. Customers are more likely to embrace this technology if it simplifies the delivery process and provides a smooth, user-friendly experience. For instance, easy access to the robot's package compartment and real-time delivery tracking through smartphone apps can enhance the user experience. Collision avoidance and pedestrian safety. Ensuring that delivery robots can navigate safely in crowded environments is a top priority. These robots must be able to avoid collisions with pedestrians, cyclists, and other vehicles while adhering to local traffic laws. Extensive testing is required to validate the safety of these systems before they are deployed at scale. Vandalism and theft prevention. Another concern is the security of delivery robots as they operate in public spaces. Robots must be designed to prevent theft or vandalism of goods. For example, many robots come equipped with secure, lockable compartments that can only be accessed by the intended recipient. Additionally, cameras and remote monitoring systems can help deter theft and provide evidence in case of an incident. Delivery robots must be designed to accommodate a wide range of environments and users, including those with disabilities. For example, robots should be able to navigate sidewalks with varying elevations or rough surfaces, as well as deliver packages to individuals who may have mobility challenges. Ensuring that these robots are accessible to all users will be essential for gaining public support. As with drones and self-driving cars, regulatory frameworks for autonomous delivery robots are still evolving. Different countries and cities have varying rules governing the use of these robots, particularly concerning their operation in public spaces. City ordinances. In some cities, regulations have been implemented to limit where and when autonomous delivery robots can operate. For example, cities may restrict robot operations during peak pedestrian hours or in crowded areas to reduce the risk of accidents. Companies deploying these robots must comply with local ordinances regarding speed limits, operating hours, and designated delivery zones. National guidelines. In the United States, states like California and Virginia have enacted laws to govern the use of delivery robots, setting guidelines for their safe operation. These regulations often include weight limits, speed restrictions, and safety requirements such as lights or signals to ensure robots are visible to pedestrians and vehicles. One of the major legal questions surrounding autonomous delivery robots is liability in case of accidents or malfunctions. If a robot damages property or injures a pedestrian, it is important to establish clear rules on who is responsible. Is it the company that owns the robot, the manufacturer, or the operator overseeing the system? As the use of these robots becomes more widespread, laws governing liability and insurance will need to be clarified. Insurance coverage. Companies deploying autonomous delivery robots will also need to secure appropriate insurance coverage to mitigate the financial risks associated with accidents. Insurers are beginning to develop policies specifically tailored to the unique risks posed by autonomous systems, but this is still an emerging area of law and business. The adoption of autonomous vehicles, including self-driving cars, drones, and delivery robots, is fraught with technological, regulatory, and societal challenges. While the promise of AVs is immense, there are still several obstacles that need to be addressed before they can be deployed on a large scale. Difficult scenarios. Autonomous vehicles, AVs, must be capable of handling a wide variety of driving conditions, including edge cases that fall outside of normal operation. These include complex environments such as construction zones, poorly marked roads, or heavy traffic. While AVs are increasingly adept at handling routine tasks, navigating these unpredictable scenarios remains a challenge, requiring further advances in AI and machine learning. Adverse weather. Autonomous vehicles often struggle in adverse weather conditions, such as heavy rain, snow, or fog. LiDAR and cameras can become less effective in these conditions, making it harder for AVs to perceive their surroundings. Developing robust sensors and algorithms that can function reliably in all weather conditions is essential for widespread adoption. Upgrading infrastructure. The successful deployment of AVs will require significant upgrades to existing infrastructure. This includes installing smart traffic lights, road sensors, and 5G networks to facilitate communication between vehicles and the environment. Governments and municipalities will need to invest in these technologies to create smart cities capable of supporting autonomous vehicles. Reliable communication networks. Autonomous vehicles rely on fast and reliable communication networks to share data with other vehicles, infrastructure, and cloud-based services. The rollout of 5G technology is critical to enabling real-time data exchange, which will improve the accuracy and responsiveness of AV systems. Without widespread 5G coverage, AVs may face limitations in their ability to operate safely in all areas. As autonomous vehicle technology continues to evolve, it holds the potential to transform industries ranging from transportation and logistics to healthcare and agriculture. However, achieving widespread adoption will require addressing the technological, regulatory, and societal challenges discussed throughout this article. Industry experts predict that while fully autonomous vehicles, Level 5, may still be several years away from large-scale deployment, incremental advancements in autonomy, such as Level 3 and Level 4 vehicles, will continue to reshape transportation. Over the next decade, we can expect to see increased use of autonomous shuttles, drones, and delivery robots in controlled environments like city centers, corporate campuses, and airports. Shared mobility. Autonomous ride-sharing services have the potential to reduce traffic congestion and make transportation more affordable. By eliminating the need for human drivers, these services could operate 24/7, providing on-demand transportation at a lower cost than traditional taxis or ride-hailing services. Sustainability. As autonomous vehicles are increasingly paired with electric powertrains, they could contribute to reducing carbon emissions and promoting sustainability. AVs may also enable more efficient transportation networks, reducing fuel consumption and vehicle wear and tear by optimizing routes and traffic flow. This comprehensive and detailed article covers the technological, regulatory, and societal aspects of autonomous vehicles, drones, and delivery robots. It explores the significant opportunities they present while acknowledging the challenges that must be overcome for their widespread adoption. As the development and deployment of autonomous vehicles, AVs, progresses, ethical considerations become central to their societal acceptance and integration. Autonomous vehicles, whether self-driving cars, delivery robots, or drones, must be designed to handle complex moral dilemmas in addition to technical challenges. The decisions made by AVs in critical situations could have profound consequences, raising questions about responsibility, fairness, and the broader societal impacts of widespread automation. The classic philosophical trolley problem is often referenced when discussing the ethical challenges faced by autonomous vehicles. This thought experiment involves a trolley heading toward a group of 5 people tied to a track, with the only option to divert the trolley onto another track, where it would kill one person instead. For AVs, a similar moral dilemma arises when a self-driving car is faced with an unavoidable accident scenario. Should the car swerve to avoid hitting a pedestrian at the risk of injuring its passengers? Or should it prioritize the safety of its occupants over others on the road? Programming ethics into AI. One of the most significant challenges in AV development is how to encode ethical decision-making into AI algorithms. Autonomous vehicles must be programmed to prioritize safety in every scenario, but determining whose safety to prioritize, passengers, pedestrians, or other drivers, can be highly complex. Different societies may have different perspectives on these moral questions, making it difficult to create universal ethical standards. Cultural and legal differences. Ethical standards are not uniform across the globe. Different countries and cultures may have varying perspectives on how autonomous vehicles should behave in life-threatening situations. For instance, in some cultures, protecting children or vulnerable individuals might take precedence over others. This raises the challenge of creating globally applicable ethical algorithms for AVs while respecting local norms and laws. Accountability and responsibility. Another ethical question is determining who is responsible when an autonomous vehicle is involved in an accident. In traditional vehicles, human drivers are typically held accountable. But with AVs, should responsibility fall on the vehicle's manufacturer, the software developer, or the owner? This issue of liability is further complicated by scenarios in which the AV must choose between 2 unfavorable outcomes. Legal frameworks will need to evolve to address these questions of accountability and responsibility in AV-related incidents. AI algorithms used in autonomous vehicles must be transparent and free from bias to ensure fairness and equality in decision-making. However, AI systems are often trained on large datasets, and the biases inherent in these datasets can influence how AVs make decisions. For example, if an AV is trained using data that predominantly reflects certain traffic environments, it may perform poorly or unfairly in different contexts. Bias in training data. If AV algorithms are trained on data that disproportionately represents certain types of traffic conditions, locations, or populations, the vehicle's decision-making could be biased. This may result in AVs performing better in affluent urban areas with well-maintained roads while struggling in poorer or rural areas with less comprehensive infrastructure. Ensuring that training data is diverse and inclusive is essential to avoid reinforcing societal inequalities in transportation. Ethical AI development. Developers of AV technologies must adopt ethical AI practices, ensuring that the decision-making algorithms are transparent and accountable. This includes documenting how the vehicle's AI makes decisions and providing mechanisms for oversight. Ethical AI development also involves creating algorithms that can explain their decisions in real time, enabling humans to understand why the vehicle made certain choices in critical situations. Public confidence in AVs. Transparency in AI decision-making is key to gaining public trust in autonomous vehicles. If users do not trust that AVs will act fairly and safely, they may be reluctant to adopt the technology. Therefore, developers must prioritize ethical transparency to ensure the public feels confident that autonomous vehicles will act in their best interests. The widespread adoption of autonomous vehicles will have significant economic implications, particularly in terms of job displacement. AVs are expected to reduce the need for human drivers across various sectors, including trucking, ride-hailing, and delivery services. This raises important ethical questions about the impact of automation on employment and how society should respond to these disruptions. Trucking and transportation. One of the industries most likely to be affected by autonomous vehicles is the trucking industry, which employs millions of drivers worldwide. With the advent of fully autonomous trucks, companies could save costs on labor, fuel, and vehicle wear and tear, leading to increased profits. However, this efficiency comes at the cost of potentially displacing millions of truck drivers, many of whom rely on these jobs for their livelihoods. Taxi and ride-hailing services. Similarly, ride-hailing services like Uber and Lyft may shift toward autonomous fleets, reducing the need for human drivers. While this could lead to lower fares and improved efficiency for consumers, it could also result in job losses for drivers who rely on these platforms as their primary source of income. Wealth concentration. As automation and AI take over more roles, wealth may become increasingly concentrated among the companies that develop and own these technologies. This could exacerbate economic inequality, as displaced workers may struggle to find new employment opportunities in an increasingly automated economy. Need for retraining programs. Governments and businesses will need to invest in retraining programs to help workers transition into new roles as automation disrupts traditional jobs. Ethical considerations around AV adoption must include plans for workforce reskilling and the creation of alternative employment opportunities. New roles in technology. While autonomous vehicles will displace some jobs, they will also create new roles in areas such as software development, maintenance, cybersecurity, and data analysis. As AV technology advances, new industries may emerge around its support and optimization, providing opportunities for workers to shift into different sectors of the economy. Service and support jobs. Additionally, the deployment of large-scale autonomous vehicle fleets will require a workforce to manage, monitor, and maintain these systems. Jobs in fleet management, robot maintenance, and AV infrastructure development may help offset some of the losses from displaced driving jobs. The overarching ethical concern surrounding autonomous vehicles is their ability to ensure public safety. Public trust in AV technology hinges on the belief that these vehicles can operate safely, protect pedestrians, and reduce traffic accidents. While autonomous vehicles have the potential to significantly reduce human error, the cause of most traffic accidents, they must be rigorously tested and proven safe before being widely adopted. Human and AV interaction. In the near future, autonomous vehicles will need to operate in mixed traffic environments, where they share the roads with human-driven cars, cyclists, and pedestrians. Ensuring the safety of all road users in these environments is a major ethical concern. AVs must be able to predict and adapt to the sometimes erratic behavior of human drivers, and vice versa. Human drivers must learn to interact with autonomous systems. Safety standards and certification. Just as human drivers must pass safety tests to earn a driver's license, autonomous vehicles should be required to meet stringent safety standards before being allowed on public roads. Regulatory bodies must develop comprehensive testing and certification protocols for AVs, ensuring that they can handle various driving conditions and emergencies. Lowering accident rates. One of the most promising benefits of autonomous vehicles is their potential to reduce traffic accidents. Human error, whether due to distracted driving, fatigue, or impairment, accounts for the vast majority of accidents. AVs, in contrast, are not subject to these limitations. By using sensors, AI, and machine learning, AVs can detect hazards more quickly and react faster than human drivers, leading to fewer accidents. Unintended consequences. While AVs are expected to improve safety, there are concerns about unintended consequences, such as malfunctioning software, system hacking, or sensor failures. Developers must ensure that AVs are resilient to cyber attacks and equipped with fail-safe mechanisms in case of technical issues. Furthermore, extensive testing is needed to ensure that AVs can perform safely in extreme weather conditions, where sensor performance may be compromised. As autonomous vehicles evolve from experimental prototypes to real-world applications, governments around the world are grappling with the task of creating regulatory frameworks that ensure public safety, promote innovation, and address the ethical concerns raised by AVs. Regulatory approaches vary significantly across regions, reflecting differing national priorities and levels of technological advancement. The role of the National Highway Traffic Safety Administration, NHTSA, in the US, the NHTSA is the primary agency responsible for regulating the safety of vehicles, including autonomous ones. However, regulation of AVs is currently fragmented, with states holding significant authority over how AVs are tested and deployed. While the NHTSA has issued guidelines for automated driving systems, it has not yet established mandatory rules, allowing states to take the lead. State-level testing and deployment. Several U.S. states, including California, Arizona, and Florida, have become testing grounds for autonomous vehicle technology. These states have passed legislation that allows AV companies to test their vehicles on public roads, provided they meet certain safety requirements. California, in particular, has strict reporting requirements, mandating that EV companies disclose any accidents or incidents involving their vehicles. Determining liability in accidents. One of the major legal challenges surrounding EVs is determining liability in the event of an accident. If an autonomous vehicle is involved in a collision, should the manufacturer, software developer, or human occupant, if present, be held responsible? US courts are likely to face numerous legal battles as EV deployment increases, and new laws will be needed to clarify liability in these cases. Insurance implications. The insurance industry will also need to adapt to the rise of autonomous vehicles. Traditional insurance models, which focus on driver error, may no longer be applicable to EVs. Instead, insurers may need to shift their focus toward product liability, covering damages caused by defects in the vehicle's software or hardware. The role of the European Commission, the European Union, EU, has taken a more centralized approach to regulating autonomous vehicles, seeking to harmonize regulations across member states. The European Commission has proposed several initiatives aimed at fostering EV innovation while ensuring safety and public trust. For example, the Commission has published a strategy for connected and automated mobility, outlining the steps necessary to facilitate the deployment of EVs across Europe. Cross-border testing. One of the challenges in Europe is creating a regulatory framework that allows EVs to operate across national borders. To address this, the EU has established cross-border testing initiatives, enabling companies to test their autonomous vehicles in multiple countries under a unified regulatory framework. General Data Protection Regulation, GDPR. The EU's stringent data privacy laws, particularly the GDPR, have implications for the development of autonomous vehicles. EVs collect vast amounts of data, including location information, driving patterns, and sensor data, which could be considered personal information under GDPR. Companies developing EV technology must ensure that they comply with these privacy regulations, ensuring that data is collected, stored, and processed securely and with user consent. Ethical AI development. The EU is also at the forefront of promoting ethical AI development, with a strong focus on transparency, fairness, and accountability. These principles are reflected in the EU's approach to regulating autonomous vehicles, with an emphasis on ensuring that EVs are developed and deployed in a manner that respects human rights and promotes societal well-being. The future of autonomous vehicles holds immense promise, with the potential to revolutionize transportation, logistics, and public safety. However, the path to widespread adoption is fraught with challenges that must be addressed through technological innovation, ethical decision-making, and comprehensive regulatory frameworks. While autonomous vehicles are already being deployed in controlled environments, achieving full autonomy in all driving conditions will require further advancements in AI, sensors, and infrastructure. Governments, businesses, and society must work together to ensure that autonomous vehicles are deployed in a manner that maximizes their benefits while minimizing potential risks. This will involve creating legal frameworks that protect public safety, addressing the ethical concerns surrounding AI decision-making, and preparing the workforce for the economic changes brought about by automation. As we look to the future, it is clear that autonomous vehicles have the potential to transform how we live, work, and move. However, the journey toward full autonomy will require careful planning, collaboration, and a commitment to ensuring that this transformative technology is used to improve the lives of all people.